Since time immemorial, humankind has looked to the stars. The universe has always been a source of fascination and of mystery. How was the cosmos born? What else might the universe contain? And where do we come from? Our universe began with a bang, the Big Bang. But what came before our universe? And what followed directly after it was born? We remain fascinated by the endless expanse of the cosmos, a vastness that transcends the limits of human imagination. And we continue to discover more about the form, shape, and size of our universe and its creation. Welcome to Spacetime, featuring astronaut and scientist Ulrich Walter and an expert on surprises the universe has in store for us. Researchers estimate that there are some 2 trillion galaxies in the observable universe, each containing some 100 billion stars. Scientists are still figuring out how all of this arose seemingly out of nothing. Cosmologists are retracing the history of the universe back to its origins. The Big Bang, the moment in which space and time were born.
Where do we come from? Where are we going? These are the big questions that the ancient Greeks were already posing 2,500 years ago. One thing I can tell you is that we are made out of stardust. But let's go back to the beginning, with the famous Big Bang, which took place some 13.8 billion years ago. People often ask, well, where exactly did the Big Bang take place? Where in outer space? That's a misleading question. The Big Bang didn't take place in outer space. Outer space was born with the Big Bang. And the question about what existed before the Big Bang is also a misleading one. Einstein's general theory of relativity demonstrated that the Big Bang gave rise to both space and time. So, time did not exist before the Big Bang. But one question does remain. What happened immediately after the Big Bang?
Our universe was born approximately 13.8 billion years ago. It all began with the Big Bang, an initial singularity, an infinitesimal mathematical point. From this point, energy, matter, space, and time all emerged, and with them, the laws of physics. This was the moment of absolute beginning. Before that, there was nothing. Today, we are able to look back deep into the past, to the time when the first galaxies were born.
This powerful drive to understand how the universe works and how it arose exists because this is a question about the origins of everything. It's not just about humankind, but what went into our creation. It's the creation of absolutely everything, time and also space. In a way, these are unanswerable questions. Maybe our brain isn't even equipped for dealing with questions like this. The Big Bang is the origin of everything. When you ask, what came before the Big Bang? A physicist would almost have to say, that's a question that makes no sense, because time itself only came into being with the Big Bang. It's impossible for anything to have existed before it. Some questions in science make no sense.
Scientists still can only describe what happened after the Big Bang.
When it comes to the Big Bang, one good question is what happened at the moment of origin. Where did the energy and matter come from? Who put it there? But physicists can't answer that, at least not yet. It's something our current theories can't explain. The same goes for black holes. Our theories of physics say there must be a singularity inside a black hole. We can't look into a black hole either, at least not yet. That's why a serious physicist would have to say they can't tell you where matter and energy come from.
In the 20th century, researchers discovered that the universe is constantly expanding. They inferred that the universe emerged from a starting point.
Physics can't explain that moment of origin. After that first fraction of a second, astrophysicists and cosmologists start asking their questions. But in a way, the Big Bang itself isn't part of our cosmos. We don't know where it came from. We can see what came after, but not what it was. Our laws of physics don't allow us to go back that far. Maybe it was quite different from what we imagined. After the Big Bang, our laws of physics kick in, and that's where we can start looking for explanations.
The Big Bang is still the prevailing model for the origin of the universe. But the theory can't explain what happened during the Big Bang, only what came after it.
So what actually happened directly after the Big Bang? Well, the Big Bang was followed by the inflationary phase, an enormous phase of expansion. To show you what that looked like, I've brought this balloon here with me. I'm going to blow it up. So imagine this is the beginning of the universe, and it was only this big. What happened then is almost impossible to imagine. This little universe, and these little dots, which represent the original particles of the universe, this balloon expanded within an extremely short period of time. In 10 to the power of minus 32 seconds, to be precise. It became absolutely enormous, about 100 billion light years, in fact. This is an area that we can't even see with our telescopes today. So what exactly was expanding back then? Well, it wasn't the particles that were expanding with respect to each other, but space itself. Meaning the particles in space. So the Big Bang created space, which then expanded in an explosive way. That's what was key about this inflation. After this inflation, the universe kept expanding, but at a comparatively slow rate. That's the state of the universe we're living in today.
When we gaze into the night sky, we're looking into the past. We see the stars as they appeared when the light was emitted. Scientists are looking ever deeper into the endless expanse of the universe, growing ever closer to the Big Bang. Telescopes keep getting larger, and their resolution continues to increase. A new super eye to the sky is under construction in the Atacama Desert in Chile. When it goes into operation in 2024, the ELT, or Extremely Large Telescope, will be the largest optical telescope in the world.
I was at the Atacama Desert in Chile, where the European Southern Observatory has a telescope. When you look up at the Milky Way there, overhead, I just can't imagine not being moved by that. I got up at night. I just couldn't sleep. I had to run out and go and look at it again. I just stood there, amazed.
Our Milky Way consists of more than 100 billion stars. To obtain the best view of the stars, scientists need to get away as far as possible from human habitation and artificial light. That's why the Atacama Desert is home to many of the world's largest telescopes. but the keenest eyes to the sky are located in outer space, like the Hubble Space Telescope. Its launch into orbit in 1990 ushered in astronomy's golden age, allowing us to peer deeper into the universe than ever before. With the Hubble, astronomers have looked out to near the edge of the universe, bringing us images of strange and compelling beauty, landscapes of light, stardust, and clouds of gas shaped by cosmic wind and radiation. Scientists are already working on a new generation of observatories. The James Webb Space Telescope will be launched into orbit 1.5 million kilometers away from Earth. The most expensive telescope ever built, the James Webb Telescope, is an international collaboration among NASA, the European Space Agency, ESA, and the Canadian Space Agency. The primary mirror, which is formed out of 18 mirror segments, is 6.5 meters in diameter. From its orbit around the Sun, the telescope will offer a view of the farthest reaches of the universe. The telescope will only reach its full size in outer space. When it reaches its final destination, a giant sun shield as big as a tennis court will unfold. The Webb telescope will peer back into the cosmic dawn to observe the birth of stars and galaxies.
Why are we out there? What are we looking for? When you look back at history, it's a very human instinct. We're curious by nature. It's our driving force. We can see it today, too. Children are incredibly curious and want to explore their world. When adults do that, we call them scientists. It's a very powerful drive, and we shouldn't underestimate it. It's important for society. Exploring new things, whether that's in outer space or on Earth or within society.
With the help of telescopes, scientists look back billions of years. But when they gaze back in time, they eventually hit a limit. The earliest light that scientists can observe occurred some 200 million years after the Big Bang. The time before that, the first 200 million years after the creation of our universe, is still hidden from us. Optical telescopes are useless here. Without light, they can't see.
In the beginning, there was only darkness. Yes, the Bible was right. We know that today because the first stars that emitted light and illuminated the universe didn't appear until 200 million years after the Big Bang. To understand that a bit better, let's take a look at this diagram. The x-axis here represents time. Every slice in this diagram depicts the condition of the universe at a specific point in time. When you look closely, you see an area that's completely dark. That's what we call the Dark Ages. And here, at 200 million years after the Big Bang, it gets a bit lighter, because this is when stars were born. They vanished again, but then new stars were born. The question that remains is this: is our universe infinitely large, or is it finite? And what shape does our universe have? To understand why the space in which we live must have shape, we need to understand the curvature of space. Picture the surface of our Earth. It's curved. If you were an ant living on that surface, you wouldn't notice that curvature. By analogy, imagine we live in a space that's curved. But because we're part of that space, we wouldn't notice that curvature. So what we have to do now is imagine that the three-dimensional space we live in is actually two-dimensional. This allows us to see that there could be three general possibilities for the geography of the universe. The first, here, is the positive curvature. It's a spherical or closed universe. So if I got into a rocket and flew out into this direction, I'd return from this direction many billions of years later. I'd fly a closed loop. Then there's the hyperbolic universe, which is curved like this. It's a pretty complicated curvature, and you can see it would be infinitely large. Then there's possibility number 3, a completely flat universe. And that would be infinite too, of course. So the only question we still need to answer is, what exactly does our universe look like?
Stars and planets emerge, galaxies fill with solar systems, clouds of gas and dust drift through space. Energy penetrates the cosmos in the form of radiation. But something else is there, something intangible that shapes the universe, a substance that no scientist has ever seen, and, as we now know, a substance that no one will ever be able to directly observe: dark matter.
Dark matter sounds very ominous, of course, but it isn't. Dark just means we don't know what it is. When something's in the dark, that means we don't understand it. We don't know what dark matter is, but physics says it must exist. That's because when we look through a telescope, we see the stars moving in galaxies. If the stars were subject only to gravitational force of matter in the galaxies, they'd move at a certain speed. But that's not the case. They're moving quite differently.
There must be another force that's being exerted on celestial bodies. A mysterious mass that researchers can only infer because of its gravitational effect.
There must be something that doesn't emit light, affecting this motion. That's why we've realized that this dark matter must exist. We can measure its impact. But what this dark matter might be, what kind of particles it's made of, physicists don't know yet. There must be quite a lot of it. In fact, there must be 5 times as much dark matter as light matter, ordinary matter. That's what our models tell us. It's astonishing. Dark matter is the norm, and we, our matter, we're the anomaly. We should be constantly tripping over dark matter, but we're not.
Dark matter permeates the universe.
If the stars are moving faster, maybe Newton's laws are wrong. But if you call Newton into question, you won't find many physicists on your side. Physicists really don't like to call the fundamental laws of nature into question. So what else could be causing the stars to move faster than Newton's laws would have it? You have to postulate that there's some other matter exerting gravitational force. Something exerting gravitational force that we can't see. The only trouble is, this dark matter must already exist at the place in the Milky Way where our sun is located. We know that our sun is moving faster than it should, but we don't know what it is. That's kind of embarrassing because this matter must be nearby, but we have no idea what it is, and we've never observed it. It's as though we haven't done our homework. Picture some guy saying, "You're nuts. You observe everything, and now you've observed something you can't explain. It's got to be around here somewhere, but you can't find it." Really? We still haven't solved that problem. Whoever manages to provide a systematic explanation for what this stuff is will win a big prize, that's for sure.
Dark matter is something we can neither see nor touch. But dark matter is the only explanation for the motion of celestial bodies and the galaxies. This invisible matter holds the universe together.
So what happens to the universe after this period of inflation? Let's take a look at the diagram. This was the Big Bang. Then we have this long dark age, which lasted about 200 million years. Then, pretty suddenly, the first stars appeared that illuminated our universe. They didn't live all that long, maybe a few million years. They were extinguished, but they catapulted all that stardust into the depths of the universe. That gave rise to the next generation of stars, which lived about 10 million years. They also catapulted their stardust into the universe, giving rise to the next generation. Each cosmic cycle took a bit longer than the one before it. After about 9 billion years, our galaxy and sun were born. We're late bloomers, you could say. But that's good, because if we'd been born earlier, there wouldn't have been as much stardust. The Earth might not have been created, and we might not exist either.
The history of our solar system also begins with the Big Bang just under 14 billion years ago. Just fractions of a second after this creation, tiny elementary particles were formed. These became the building blocks for hydrogen and helium, the lightest elements. The new universe continued to expand. The cooling of the universe, along with gravity, helped transform this matter into the first galaxies. As vast clouds of molecular gas continued to increase in density, the first generation of stars were born. Very large and very hot, the first stars died young. These first stars lived only tens of millions of years before they collapsed. Supernova explosions then dispersed the elements that would become the next generation of stars. New stars can only be born from a supernova, an explosion that ensues when a massive star collapses and explodes. These brilliant bursts of light in outer space mark the death of a star and the birth of new celestial bodies. The power of a supernova is what enables the formation of elements that are heavier than hydrogen and helium.
The lead and uranium here on Earth don't come from the sun. They come from supernova explosions. So you can see that we arose in an era that was very violent. There were suns that produced iron, but there were also supernovae, which generated lead, uranium, and other heavy elements, bismuth, and so forth.
Terrestrial planets such as our Earth require such heavy elements in order to form. A supernova explosion sends an enormous amount of matter hurling into outer space. The matter is mainly oxygen, carbon, silicon, and iron. Together with interstellar gas, it forms the dust clouds that can be observed through our telescopes. These clouds become the cradle from which new stars are born. But some of the particles of dust collide with one another and form clumps. These clumps grow ever larger, becoming first embryonic planets and then terrestrial planets. In the early period of our solar system, a disk of gas and dust rotated around the sun. Like a giant wheel, this disk orbited the star at the center of our solar system. This was the cradle of our planetary system. The gas gave rise to Jupiter and Saturn, the two gaseous giants that were and still are crucial to the development of our solar system. The discovery of these disks of dust surrounding young stars helped solidify our understanding of the origins of our solar system.
We just don't know what's going on out there. We don't even know what's going on in our solar system. Even the planets in our solar system differ. We have gaseous planets, terrestrial ones, ones with and ones without a ring. Some rotate in one direction, some in the other. I think it's curiosity that drives us to try to understand this and everything else that exists in our enormous universe. Is there some origin, a Big Bang? What existed before the Big Bang? Physicists say that's not a viable question. But they're fascinating questions, and of course, we want to understand them.
From the beginning, humans have sought to understand and explain their world. The cosmologies devised by religions were also a form of doctrinal teaching. Many ancient cultures and creation myths depicted the world as a flat disk, but even in antiquity, the realization that the Earth was a sphere prevailed. There is no edge of the world that we could fall off of. However, the position of the Earth within the universe was long a matter of dispute.
It took a while for us to understand that the Earth's position didn't have anything to do with theology. In the past, that wasn't so clear. We assumed that humans must be at the center of all creation, the pinnacle of creation. Aristotle had something to do with that. He loved the idea of a hierarchical universe. The belief that humankind was at the center proved very appealing, and it didn't leave room for much else.
The scientist and philosopher Aristotle believed in a geocentric model of the cosmos. For him, the Earth was the origin and center of the universe. The Christian Church adopted this worldview and defended it with vigor. This model held sway for nearly 1,500 years. In the 16th century, Nicolaus Copernicus placed the Sun at the center of the universe. The planets, including the Earth, revolved around it. In the early 17th century, Galileo Galilei was the first to use a telescope to observe the heavens. This marked the beginning of modern astronomy.
The sun was put at the center, which led to an entirely new perspective and understanding. Telescopes made it possible to look out into space and see what was out there. Until then, it was all speculation, and everything was understood within a humanistic framework. Suddenly, we could see all these things that we could never see before: the phases of Venus, the moons of Jupiter, and how they orbited Jupiter. So many things were suddenly visible. This process of observation was the birth of astronomy. The next step was not just observing, but trying to understand.
Our understanding of the world has been profoundly shaped by astronomy. It is regarded as the oldest science. The path of the sun across the sky during the day, the bright stars at night, the phases of the moon and the motion of the planets in our solar system. All this has always sparked our innate curiosity.
Our knowledge of the universe is increasing enormously, and it's increasing at such a rate that the astronomy textbooks basically need to be rewritten every few years.
The dawn of the space age allowed us to reconceive the relationship of the Earth to our solar system and the entire universe. Today, astronomers send observatories into outer space and conduct research outside the spectrum of visible light. Telescopes that can observe X-rays, gamma rays, infrared and other spectral ranges offer new insight into the cosmos. Each part of the spectral range opens a different observational window into outer space, giving rise to new discoveries. These telescopes are designed to observe phenomena that take place at the end of a star's lifespan, such as exploding stars, supernovae, neutron stars, and black holes. Using the NASA New Star telescope, scientists were even able to observe two colliding galaxies.
What do the galaxies in our universe look like? Well, they're usually shaped like a disk, just as we see here. So how did it all begin? Imagine an enormous cloud which collapsed in on itself. As it rotated, this cloud collapsed into a disk. That's what we see right here. There are stars in this disk, as well as many dark clouds. These dark clouds are made out of stardust. But most of the stars are here in this bulge in the middle. Why is it round? Because that's where most of the stars are gathered. Right in the middle of this bulge, in the middle of every galaxy, there's a huge, fat black hole, which is many million times the mass of the Sun.
A black hole is the densest form of matter that exists, the densest matter we can imagine. In 1974, a powerful radio source, the Sagittarius A star, was discovered at the very center of our galaxy. By the 1990s, scientists had concluded that it was a black hole. Black holes cannot be observed directly, but they affect their surroundings. It is this effect that astronomers and astrophysicists observe and analyze.
We can see that stars in the middle of the Milky Way, in the Sagittarius constellation, are moving along an elliptical path around a point, but there's nothing there. Normally, a planet orbits a star. You see the star and see its gravity maintaining this planet in an elliptical orbit. When you look, you see nothing. Something's exerting gravitational force, but we can't see it. We know it must be very heavy because it pulls entire stars into its orbit. By observing the star's path, we can calculate the mass of that center, which ends up being several billion times the mass of the Sun. We suspect there are supermassive black holes in galaxies, and in fact, there's evidence for that.
By conducting research on the universe, we are also engaged in a search for our own origins. Is our own existence simply a coincidence? Just a few decades ago, many still believed that our solar system is unique, but it turns out that it's just a tiny grain of sand on an immense galactic beach. Today, scientists believe that each star could have its own planetary system, and they continue to discover ever more planets with conditions similar to those here on Earth.
The universe appears to be teeming with planets. We found planets at an ideal distance from their star. They're not too hot or too cold, nice and cozy, like here on Earth. We found many planets like that in the universe. So the basic conditions that gave rise to life as we know it appear to exist in many places. Then we need to check, do these planets have an atmosphere? And what's its composition? Is there carbon dioxide, oxygen, methane? Normally, this mix of gases would be unstable, unless it's being maintained by organic processes like here on Earth. If we found that mix of gases in a planet's atmosphere outside our solar system, we'd be able to say we've discovered life on another planet. That discovery isn't all that far off. The newest telescopes headed into outer space will be able to detect atmospheres on small planets. I'd say we're 10 or 20 years away from this moment, at most. That's very exciting. I predict that within that time frame, we'll discover life elsewhere in the universe.
Finding life in outer space would be the greatest discovery of all time. It would provide an answer to one of humanity's most enduring questions. Are we alone in the universe? Is there another planet similar to Earth with conditions favorable to life? To chart our galaxy, the European Space Agency launched the Gaia space probe in late 2013. The satellite is creating a precise map of the astronomical objects in the heavens. Using this data, astronomers plan to make a 3D catalogue of the Milky Way, which will provide new insights into the origins and evolution of our galaxy. Gaia is positioned 1.5 million kilometers from Earth on a Lagrange point, a spot where the interaction of gravitational forces creates a near equilibrium. At this point, the gravitational pull of the Sun and Earth and the centrifugal force of the satellite orbiting the Sun cancel each other out. The probe remains parked at this stable position, needing only a minimum of fuel to maintain its location in space. Gaia is measuring the positions, motions, speed and brightness of nearly 1.7 billion stars in the Milky Way. The data will provide a detailed catalogue of our cosmic surroundings.
Gaia will carry out precise measurements of billions of stars and catalog them, giving us a huge trove of data. The first catalog has already been released. We'll measure those positions year after year and observe those changes. We'll be able to see some variations in brightness and even generate spectra and detect signatures to an extent. That will give us a huge trove of data, and we can apply statistical methods to that big data. Perhaps to examine how the sun flies around the galaxy or what dynamics exist. Which stars go where? Are there stars we haven't found yet, or stars on a collision course with the Earth? Those are the kinds of questions we'll be able to ask. Gaia has also located some very dark bodies on the outskirts of our planetary system. Now that we know where they are, we can observe them and try to understand them.
Though 1.7 billion catalogued stars seems an impressively large number, this corresponds to only about 1% of all stars in the Milky Way. A figure that illuminates the vastness of our galaxy and the incomprehensible expanse of the universe.
What does the future of our universe look like? Well, we know that each type of curvature has a particular future. Let's take another look at those curvatures. Imagine the universe is a sphere with a positive curvature. We can show the sphere would continue to expand and eventually shrink back to nothing, back to the Big Bang, as it were. That would mean the universe is finite. This saddle shape here would be very different. We'd have a universe with no bounds that would expand forever. And here's the third possibility, the flat universe. This universe would also expand forever. And here's the thing. In April 2000, we discovered the geometry of the universe. How did we figure that out? It was thanks to background radiation. In the 1960s, we discovered that microwave radiation is constantly hitting Earth from outer space. This radiation has an inner structure. That means when I look in different directions, the intensity of this radiation will vary somewhat. When I depict those variations in color, I get the structure you see here. And now comes the decisive point. Theoretical scientists have been able to show that the distance between these points allows us to derive the curvature of space. That's what they did in April 2000. What they showed is that we live in an absolutely flat universe. And that suggests the universe will continue to expand forever.
Background radiation was discovered almost by accident in 1964. Physicists Robert Wilson and Arno Penzias were mapping radio signals in the Milky Way. An odd buzzing noise interfered, which turned out to be microwave radiation from outer space. The two scientists had discovered cosmic background microwave radiation, an echo of the universe at a very early moment after its birth. The discovery of this faint whisper was a milestone in our understanding of the cosmos.
Looking deep into outer space, observing the speed and direction at which galaxies are moving, investigating dark energy, dark matter, black holes. How does it all fit together? These are all fascinating questions, and we still don't understand them at all.
Scientists are on a journey to the limits of knowledge in search of the blueprint to the universe. Although they continue to acquire new insights at an ever faster pace, much more remains to be discovered. The universe still holds many mysteries waiting to be unlocked.
Today we know our understanding of the universe is very incomplete. For example, we know that all the matter we see around us appears to make up only 5% of the universe. Then there's another 25% which we know is there. That's dark matter. We can observe its effects, but we don't really know what it is. It's still a black box for us. The remaining 70% is even more mysterious. Physicists have said it's dark energy. That sounds awfully dark. That's what's causing the universe to expand in a way that we observe. Normally, you'd expect it to expand more quickly or more slowly. To arrive at the rate of expansion that we observe, we've had to introduce this dark energy, and that makes up 70% of what we believe exists in the universe. If you add it up, our theories explain only 5%. The remaining 95% is still unclear. For scientists, this is a golden age.
On September 14, 2015, scientists in the US observed gravitational waves directly for the first time. That opened an entirely new window to the universe. It was evidence that the fabric of space and time is not static and unchanging.
It's the same as always. Einstein was right. Also about gravitational waves. So you're probably wondering, what is that exactly? Well, it has something to do with space. Imagine that our three-dimensional space is covered with a two-dimensional surface, like the surface of this water right here. This surface could be disturbed, which is what I'll do. Watch. When I touch it, a wave is formed, which ripples outward. That's exactly how you should picture a gravitational wave. It's what happens when elastic space is disturbed. Einstein said that space is elastic. If I bump it, I'll create a ripple, which moves in a three-dimensional fashion through space. That's a gravitational wave. Einstein said about 100 years ago. A few years ago, we detected one. So, they really do exist.
Albert Einstein had predicted these gravitational waves, but it would take another century for scientists to demonstrate their existence. The gravitational waves originated 1.3 billion light-years away. They were oscillations in the fabric of space and time, generated by a cosmic catastrophe. By the time it reached Earth, the distortion measured only about 1/1000th of the diameter of an atom.
We've known for quite some time that Albert Einstein's theory that an accelerating object will emit gravitational waves is indeed true. We've been able to demonstrate that here on Earth. We've now designed a mission called ELISA, in which we'll send 3 probes into space. These 3 spacecraft will measure gravitational waves coming from various directions, which will allow us to determine where the waves are coming from, at what speed, and so forth. It's a new and exciting way to observe outer space.
In September 2015, astronomers observed the collision of 2 black holes. One was 29 times and the other 36 times the mass of the Sun. They crashed into each other, merging into a single black hole. This collision sent out a powerful burst of gravitational waves, causing ripples in the fabric of space-time, which continued to move onwards through the universe until they were detected on Earth with the help of 2 lasers. The ripple of the gravitational wave was so tiny that it could only be observed using the high-precision detectors placed a certain distance apart. A tiny deviation of the laser beam between the 2 arms detected the appearance of a gravitational wave. This direct observation was an extraordinary event. The physicists who detected the waves won the Nobel Prize. gravitational wave astronomy marks a new era in the study of the universe.
Detecting these gravitational waves suddenly allows us to investigate parts of the universe we normally can't see. We can draw inferences about processes we normally wouldn't be able to observe, like the merging of two black holes or two neutron stars. We assumed that could happen in theory. If black holes exist, then why couldn't there be two? Or maybe they could somehow merge. You can imagine all sorts of things in your theories, but now we know this actually does happen in the universe. They do merge, and more often than we had suspected. Gravitational waves have allowed us to prove something that used to be just speculation. It's opened a new window, given us a new view of the universe. That's what we'll be doing over the next years and decades.
The next sensational discovery followed in August 2017. For the first time, scientists observed the spiraling crash of two neutron stars. The merging stars generated gravitational waves, gamma-ray bursts and light waves, which the scientists were able to observe and analyze.
Gravitational waves can generally only be detected when there's a huge burst of energy, which is then transformed into gravitational waves. That only happens during cosmic catastrophes, like the melting of neutron stars or black holes, something of that magnitude.
Neutron stars are very small but extremely dense. Although they are just 10 to 20 kilometers in diameter, their mass is about twice that of our Sun. The neutron-star collision took place practically in our own galactic neighborhood, in galaxy NGC 4993, some 130 million light-years from Earth.
What will happen to our universe? And above all, how will it end? Well, cosmologists aren't in agreement about that. They've developed two basic scenarios. Both begin with the following situation. These cosmic cycles will continue for some time, but not forever. Perhaps for 20 or 30 more cycles, and then they'll end, because the hydrogen will have run out. And if there are no new stars, and no new Earths, and no new civilizations, everything will die out. The universe will keep expanding. It will get colder, and everything will head toward what's called the cold death. That's the first scenario. The other scenario looks like this. The universe will continue to expand, but not slowly. It will expand faster and faster. This expansion will keep accelerating, and in the end, everything will rip. Not just the Earths, the planets, but everything will rip down to the tiniest grain of sand, the tiniest elementary particle. This massive destruction has been dubbed the Big Rip. That's the second scenario. Whichever happens, the cold death or the Big Rip, I can promise you it will take forever, close to eternity. So you can rest easily tonight.
Just a few hundred years ago, we believed ourselves at the center of the universe. Since then, we have come to realize that we are little more than an insignificant speck within a seemingly endless cosmos. We continue to gaze ever more deeply into the universe and have succeeded in decoding some of its mysteries. Today, we live in the golden age of astronomy, but what we have discovered thus far is only the beginning.